We already talked about digital connections, so we're going to talk about analog connections this time. So we'll look at connector types. We will look at sources of hum and noise in audio measurements, balanced and unbalanced analog circuits, some tips for connecting equipment together, and also for testing and verifying connection problems. I have a few demos here that we can play with as well, so hopefully we won't be getting too sleepy before lunch. Okay, so there are many connector types and two basic connection circuit types. There's the balanced, which is usually pro audio and broadcast, or unbalanced, which is usually consumer audio or very low impedance such as power amp outputs. Connection problems are the most common source of testing difficulty. Some tests may appear okay, and others appear wrong when the connections are incorrect. So incorrect or poor connections may not be immediately apparent, and you need to do some troubleshooting. This shows the balanced analog audio connectors. So we have the most common type are the XLR, female and male, shown here. And this is the AES 14 standard. So pin 1 is the cable shield, which typically carries the ground. Pin 2 is the positive going phase, or the high. And pin 3 is the negative going phase, or the low, or inverted phase. The next one here is called a 1/4 inch phone or tip ring sleeve. So this would be in metric, I guess, 6 millimeters roughly. And they're often abbreviated TRS for tip ring sleeve. So the tip is positive going phase, the ring is the negative going phase, and the sleeve, number 3 here, is the cable shield. There are also banana connectors. Sometimes you'll see a double banana, which is on one connector, and it'll have a little tab, which shows the low side. There are mini XLR, LEMO, and some other connectors, and then you have things like these screw terminals, which are sometimes used on the output of power amplifiers. And they can be marked with the plus and minus, or chassis, or GRD for ground. These show unbalanced analog connectors. So the RCA phono plug is the cheapest and the least reliable. These are the ones that we don't like very much because the signal is on the center conductor, and when you connect an item together, that's the first thing to touch. It would be better, like a BNC connector, if the shield touches first, and that way any charge buildup can be grounded out before the signal connects. So it's less likely to damage the equipment. There's a 1/4 inch, we looked at these earlier, TRS that is used for stereo headphones. And there's also 2.5 and 3.5 millimeter versions of this for headphones and speakers. We have also, so TRS is stereo, tip ring shield. We have a 1/4 inch tip and sleeve. This would be for mono headphones or speakers typically. And then the 2.5 and 3.5 connectors can be either stereo or mono. And then I guess there's also an AV connector, which has it has actually 4 conductors. There's a tip for left, a ring for right, a second ring for video, and a sleeve for ground. And then similarly, screw or clamp terminals are most often used for power amplifiers, but they occasionally can be line level. And now we'll look at hum and noise sources and causes. So we can get hum and noise from electric fields. Fluorescent lights, such as these in the room here, put out high frequencies. Some older computer monitors and high voltage sources. We can also get signals from radio stations and cell phones. And this will capacitively couple into any unshielded, non-zero impedance conductor, a high-pass filter characteristic. So shielding is very effective. All varying magnetic fields induce electric potentials and vice versa. An electric field will induce a magnetic potential at right angles to the path of the flux lines. So the takeaway here is to make sure that the signal lines cross the AC mains lines at right angles, and that will minimize the induction. The induced potential is proportional to the loop area. So it's always a good idea to twist signal pairs of wires. That minimizes the loop area and cuts down the induction. And then there's a special type of quad filar or star quad cable that works well, but it has a higher cable capacitance. So many of the cables that we use at Audio Precision are this quad filar. They have 2 pairs of cable for each signal path that are twisted together. Another source of hum and ground is what we call a polluted ground. That's a poor physical earth connection. And the AC mains current is in the ground system. So how does noise get into the audio? The first path is for a poor connector contact. If you have a high contact resistance between the 2 connectors, that can cause a problem. The AC mains related hum from a ground loop. We'll talk more about ground loops in a later slide. The AC mains hum picked up inductively by a cable. And then we have radio frequency or RFI interference related. So you can have the AC buzz from a television vertical interval for old analog TV and horizontal sync at these frequencies. They're higher frequencies with CRT-based monitors. And then you can also get frequencies picked up from lamp dimmers. So the dimmers or sometimes these motion sensors that are infrared, they can emit higher frequencies. And they can pollute the AC mains ground by adding a signal into the ground. This is about ground loops. So wherever there are multiple ground paths between 2 or more pieces of audio equipment, a ground loop is said to exist. So here we have one piece of equipment on the left with a source impedance connected to a second piece of equipment on the right. Both have a chassis ground, but there can be a loop in the system called a ground loop. So the loop in this example involves the unbalanced audio signal connection and the safety ground wiring between the 2 devices. Typical consumer systems can have many ground loops. So quite often these consumer devices like disc players and AV receivers do not have a 3-pin connection. And there can be multiple power connections and multiple ground loops in the system. For large facilities, it's a good idea to use what's called a star grounding system. So here you have a single point of contact and all the pieces of equipment have a large scale conductor connected to the same ground. So the connection of each piece of equipment is like a star, and that's why it's called star grounding. And if you have a very large facility, you could use a series of stars all connected to a main ground. So this is, in this bullet, it's called a star of stars because you have many separate stars all connected back to the main star. And in this case, you want to use a large conductor, ground conductor, something like a maybe 10 or 12 gauge wire. And at Audio Precision, we sell grounding kits that are these large conductor wires. So there's a technique called brute force grounding. This idea is to have a much lower impedance connection so that any current caused by the chassis potential differences is carried mostly in the cable. So you'll notice on our front panel and in the back panel of our analyzers we have these banana connectors that can be used to accept the ground terminal. It's also a screw lug. And the idea is you just use a large ground strap between the two pieces of equipment and ensure that the potential flows through that larger conductor. So it's a multi-strand ground cable with, for short runs, it can be number 10 or number 12 stranded. And for large facilities or longer lengths, they can use something even like a welding cable, which is a very large diameter conductor. This is called 0 or double 0, so it's a really large conductor. The circuit is a current divider, and the values depend on the relative ground cable and signal cable impedances. This is the concept of telescoping ground. So when you have a series of equipment, pieces of equipment connected together, each signal cable each signal cable shield is grounded only at one end. So here we have the two items of equipment connected, and the ground would be connected at this end, but there would be no connection to ground at the other end. So the one way to do this would be to disconnect the pin inside an XLR connector, for example. And that helps to avoid ground loops by ensuring that there's one main path to ground. If you connected the connector here, the shield, there's the possibility of a ground loop existing along this wire. This shows the characteristics of a balanced connection. So in this case, the two signal lines have equal impedances. Both the source and the load impedances must be matched. So here we have a twisted pair of cable. And you can see we have the positive going signal and the negative going signal. And the interface takes the difference between the two and subtracts out the noise and reinforces the signal. So the intended audio signal is differentially referenced between the two signal lines, and it's not referenced to ground. The voltage symmetry is not a requirement of the balanced connection. Noise and hum sources are usually common mode with their references being ground. Since the shield is not part of the signal path, ground loops have little effect on the differential audio signal. They can be avoided totally by connecting the shield at one end only. So this is why you'll see balanced connections often used in professional audio, and especially with microphones, because microphones have a very low-level signal and they have to be amplified up quite a bit. And you want to minimize the noise because if you apply the gain to the microphone signal, you're going to be applying the gain to the noise as well. CMRR stands for common mode rejection ratio. So that's the relative rejection of a connection to a common mode signal. Stray capacitance in the circuit normally makes this decrease with frequency. The complex impedance of the cable becomes a more important factor with increasing frequency. So you can see here we have the differential signal with a little bit of noise on it, and if we take the difference between those two, those will be subtracted out. For balanced grounded sources, this really means that the impedance balanced to ground. So we have an active balance driver, such as in the APX family, where half the output voltage appears between each line and ground. So the source impedance over 2 is in each of the two differential signal chains. Our older instruments use a transformer with center tap grounded, like our 2722 series, and that would be corresponding to the circuit diagram over here. In this case, the output voltage appears between each line and the tangential balance may not be equal. Sorry. The two signals are usually symmetrical, but the cable shield can be a part of a ground loop. For balanced floating sources, these are usually transformer coupled. However, semi-floating active balance outputs are also possible. There's no intended ground reference except for the stray capacitance. Semi-floating designs often have a shunt resistive component. So measuring from one side to ground often gives spurious readings. A ground loop in the signal is not possible, but the cable shield can be part of a ground loop. And then signal characteristics for unbalanced connections. So the signal is carried on one line in reference to a ground line or a chassis connection. Only the signal line has a specified source impedance. The ground line is assumed to be zero source impedance, and that's why it's called unbalanced. The signal is in the same mode as the hum and noise, so there's no noise immunity, and a ground loop is likely. So unbalanced grounded sources, typical of most consumer electronics connections, and this would use the this RCA type phonotype connector that we talked about before. The signal is carried on the one line in reference to a ground or chassis connection, making it inherently very sensitive to ground noise. Unbalanced floating sources, this requires either an output coupling transformer, floating, or a very tricky output drive circuit, semi-floating. Some audio precision products use a semi-floating design in the unbalanced output configuration. So this would be talking about our System 2700 family, probably, not for the APX. So for connecting equipment together, typical connections would be a balanced output to a balanced input. So this is the best interface and has the best noise immunity. The accuracy of the source and load impedances are important. They directly affect the common mode rejection ratio performance. Grounding the cable shield is best only at the source end for maximum rejection of high frequency ground noise. And consider the effects of cable capacitance. So this shows the source with the matched impedance on each conductor, and it's grounded at the source end but ungrounded at the receiver end. Now this shows a balanced audio precision generator output connected to an unbalanced device under test input. And this is not recommended. Floating may be okay at low frequencies, but common mode capacitance will cause the generator amplitude to roll off at higher frequencies. The ground is very bad, and one half of the output is shorted. So this is for an active output like the APX, and the front slide is for a transformer coupled system like the 2722. So you can see here, this is the measured level versus frequency, and it varies with the source impedance, these different colored curves, and it also rolls off at higher frequencies. Effective floating of the resistance and capacitive elements in the device under test output stage will cause its amplitude to vary at low frequencies and to roll off at higher frequencies. This is an unbalanced generator output to a balanced device under test input, or an unbalanced device under test output to a balanced analyzer input. This can be okay, but noise immunity is limited since the source impedance is not equal in the two lines. And here we have an unbalanced output to an unbalanced input. It's as intended, but it's the worst possible connection. There's no rejection of ground noise at all. Multiple connections of this type create ground loops, increasing the sensitivity to magnetic fields. And audio cables are often made with low or even poor quality shielding at RF frequencies, enhancing the possibility of radio frequency signal detection problems in the audio output and or the audio input circuits. So we'll talk about testing and verifying connection problems. There's the brute force approach that we talked about earlier, just to use an additional separate, better ground connection, a high gauge wire. There's a technique to filter out the low frequencies using A weighting or a 400 hertz high-pass filter to check for significant improvement. And you could change the analyzer configuration, but you need to be careful about not creating other problems. You can also listen to the source, and you can analyze the spectrum using the FFT analyzer. So the brute force ground, this shows an example of a signal measured in the frequency domain without grounding and with grounding. So in this case, a number 12 or number 10 heavy gauge wire with many strands and high quality is connected between the device under test and the ground. You can see how we have a signal at about 60 hertz here. This would be the line frequency, and it's dropped significantly with the brute force ground in level. So with spectrum analysis, we can look for a very detailed look at possible problems. You can look for AC mains related frequency and its harmonics. A higher AC level in one channel means the internal electronics is closer to the AC source. And you can look for second, fourth, and even order harmonics usually indicate a power supply filter inadequacy. Those would be the even orders. The odd orders, third, fifth, and higher, usually indicate a nonlinear magnetic field such as a power transformer. It's not uncommon to observe AC mains related harmonics extending up through 2 kilohertz in frequency. Higher frequency noise and spurious spikes can be created by motors and light dimmers, and these often jump around in the spectrum and they may not be stable with frequency. There's also switching power supply noise and Class D power amplifier noise. That's not a connection problem, it's just a problem in general. So some of the tips. Radio frequency interference problem. A cable shield is just an antenna, particularly in the VHF range of the radio spectrum. With only one end grounded, there can be a significant RF potential at the ungrounded connection end. So one way to get around this is to use a very short lead capacitor from the shield to chassis ground. And in the case of VHF radio frequencies, a 0.001 microfarad high quality capacitor connected between the shield and ground can be used. You should be careful, however, an unfortunate choice can cause resonance and make things worse. All capacitors have a self-resonant frequency above which they appear inductive. The XLR pin 1 connection, so we assume that the XLR pin 1 is connected to chassis ground, but where? The shield pin 1 current should go directly to chassis ground, not through any internal analog signal circuit ground. So the lowest possible resistance and inductance connection is best. And you want to minimize the path length between that pin 1 on the XLR and the ground within the device. It's critical for good radio frequency performance. Balancing an unbalanced output. If an output is unbalanced, it's possible to improve things by inserting a resistor equal to the output impedance in the ground line at the device under test end. This creates a balanced source impedance condition, so induced noise is equal and can be canceled by a differential input. This works even though only the output signal voltage is single-ended. So we have here a single-ended unbalanced connection, and we're inserting a resistance between the shield and ground to try and balance with the source impedance. Use good quality shielded twisted pair cable and ground the shield as shown here in the diagram. So Belden 8451 or equivalent, it's a 22 gauge twisted pair within a foil shield with a drain wire. So that's it for the slides. I have a couple of demonstrations here that I'm going to set up. So yeah, so one of the things I want to do is this is a little device for, it's a handheld voltage connector, and you can just carry it in your shirt pocket. You just turn it on, and it can be used to check for voltage. So if we get it close to something, it'll just beep and flash like that. And just for a demonstration here, I have this device under test, the D to A and A to D converter. I've disconnected all of the signal lines, and you can see there's no high field there. Let's turn it on. So what I'm going to do is I have a little adapter here for the IEC power mains, and inside the ground pin has been removed. So I'm going to connect it such that it won't be grounded. So let's try that again. Well, this worked in my hotel room yesterday. Maybe it's grounded somewhere else. Okay, well, so much for that one. But we did have some problems. You know, we sell audio analyzers all over the world, and quite often they're used in China for production test applications. And we've been having problems with the USB chips blowing up in China. And so we sent over a couple of our engineers and technicians, and they took some of these along and checked the wall sockets, and almost none of the AC mains plugins were adapted anywhere, were grounded. And that can be a real problem because you can get these ground loops in the equipment, and high currents can go through the USB cable, causing problems. It also causes a problem with the audio measurements, of course. So I have one other demo that I'll see if I can get working. So normally with a good quality XLR cable, you're going to have at least one connector for each side. They're going to be twisted pair and have a shield. And one of my colleagues made up this cable, which is, it's got no shield wire on it. And it's not a twisted pair, so it's just like a lamp cable. Two conductors, no twisting, and we're going to check for noise immunity. And I haven't done this demo before, so we'll see how it goes. Hopefully I won't blow anything up. So let's have a look at balanced out and one channel. Let's just try loopback first. Have a look at the FFT here. So that's in loopback, and let's just turn on a signal. So we see a nice clean FFT. Now if I take it out of loopback and look at the balanced connection, so still a pretty good signal, and this is going through that cable with two wires that are untwisted and unshielded. And now what I'm going to do is plug in this device. It's a magnetic device for erasing tapes, I think. It's a very, very high magnetic field. And we'll see what that looks like. Hopefully nothing will blow up. So I think you could see the hum components and the harmonics of the hum being picked up, especially as I bring the device closer to the cable. So now I'm going to switch that cable for a regular XLR cable, and we'll see what we get. So in this case, the cable is lying right on top of the magnetic device. And you can see there are some components, but not nearly as bad as we were seeing before. So I think in the program this was called digital wired testing. But we're going to try and focus a little bit on measuring analog to digital and digital to analog converters. So the scope of the presentation, the AES 17 is a standard for digital audio device measurement, and we will show how to characterize digital devices. So digital to digital devices, I think I covered that yesterday when we looked at HDMI. I showed you the metadata recorder and the bit test for bit accuracy, so we probably won't cover that again today unless someone has questions. We'll look at analog to digital converters, or ADCs, digital to analog converters, or DACs. And yeah, we talked about bit comparison and metadata. And then A to D and D to A, level and gain measurements, digital filter response measurements, noise measurements, and distortion measurements. So what I might do is, after the presentation, go through a lot of the measurements that are in this tech note, and we could look at those together if you like on this device that we have to play with. So as I mentioned yesterday, we have this tech note, Measuring A to D and D to A Converters with the APX 555. It's a very good resource. You don't have to use the APX 555, but it does have the best performance. So if you have a very high performance DAC or A to D converter, you might want to use that analyzer. You can download this for free at ap.com. If you haven't downloaded things from our site before, it's very simple. You do have to register, but it's a free registration, and you can just log in the next time. You only have to register once. This includes several project files for testing ADCs and DACs, and there are two sample rates covered, 48 kilohertz and 192 kilohertz, but they could easily be adapted to other sample rates like 96 or any others. Okay, so we talked about the bit comparison yesterday, did a little demonstration. So in this display we can look at the active bits or the data bits, and we also have a measurement for the bit accuracy. There's another measurement that I didn't talk about. I think I could demonstrate that. Yeah, why don't I do that? I'll demonstrate that measurement. So let me escape out of here. Something that we didn't cover. So I'm going to go into sequence mode. And we'll just set up a digital connection. So let's look at HDMI source, and I'll just set it on loopback. And just as a check, we get 8 channels of audio. So now we're getting a nice digital connection. So a measurement that I didn't talk about, it is called compare encoded bitstream to reference. And this would be used for testing encoded audio files. So for example, if you have a Dolby or a DTS stream, you can load a waveform. And let's see, I'm not sure if I have any encoded ones here, but basically you would load a waveform file that is a DTS waveform or a Dolby waveform, run it through your device, and the system will acquire the file, and it will show you any frames that mismatch. It will tell you if there are any errors between the stream that is expected and the stream that's coming in. So this is a great way to test things like disc players or devices that output encoded audio. It will show you the received frame count, the valid frame range, the skip frame range, any excluded error frames, error frame numbers, and an error frame description. So I mentioned yesterday that the HDMI interfaces uses this high definition content protection, HDCP, and because of that, there are restrictions of, we're not allowed to record the file that comes in over HDMI if it's HDCP encrypted. So we have to bring it into memory and just keep a very small piece in it in memory and look at it bit by bit, compare it to the reference stream. So that's another resource for you for testing encoded audio. Back to the program. We did talk about the digital error rate measurement. So again, this is a signal that we generate inside the APX analyzers. It's called the bit error test. And so it's just a pseudo-random sequence, but it's a known sequence. The analyzer knows the sequence. So on the input side, every time it acquires a bit, it will shove it into this algorithm to compute the next bit, and it can tell you if you have a bit accurate connection. Now, what you can do, if you do have a bit accurate connection for a digital in, digital out device, then once you've verified that the system is bit accurate, there's no need to do any audio tests anymore. If it's not bit accurate, things like sample rate converters can't possibly be bit accurate because there are filters involved and the bits get moved around. You can still have very high audio performance. Now in that case, you can't use a bit error rate test, and you would have to resort to conventional audio measurements like measuring the level, the frequency response, the THD plus N, and so on. We did talk about the metadata recorder. I did a little demonstration on that yesterday. Actually, one resource that I would like to point out as well is if you're doing open loop tests, for example, testing a media player or a PC, and where the audio analyzer is not the source of the signal, you often need files to load onto the device. So there's a resource that we have, which again you can download from our site. Yeah, so there's this little program that's available on our website called Waveform Generation Utility. And as you can see, it's very small. This is about 108K. Now, in the old days, we used to post these files on our website that people could download, and they were at sample rates up to 192 kilohertz. And actually, this is an old version of the utility. There's a newer version available. But the way this works is there's a variety of signals here. I think there are about 30. These ones have a sine wave at 0 dB, minus 20 dB, minus 60 dB. There's silence dithered, silence undithered, bunch of crosstalk waveforms and so on. And included in this is the bit test signal. So if you want to test the bit accuracy of a device that we can't connect an input to, you can load this waveform on the device, generate it back into the analyzer, and test for bit exactness. And the way this utility works is you choose a folder that you want to generate the waveforms to. You can check all of them. You choose the sample, the bit depth, and the sample rate. Usually I make a new folder, and when you click this button, it will create all of these waveforms on your PC. So this is a very useful little utility that's free, and you're welcome to download it from our site. The newer version has some additional capabilities. There's a signal in there for multi-channel wave files, Inside the APX analyzers, we now support multi-channel extensible WAV files. And there's a very nice signal that has a different frequency on each of 8 channels that you can play into your device. Let's go back to the program here. Okay, so we talked about metadata yesterday, AES-3 digital balanced, unbalanced, and optical, as well as HDMI and HDMI ARC carry metadata. It contains information about the audio. So for the AES-3 interfaces, it's composed of 2 parts: data bits, status bits, a set of defined fields and values such as sampling frequency, sample word length, copyright, channel number, etc. And then user bits, the usage depends on the device. Examples include scene and take numbers and notes. Yeah, I think we already covered the HDMI audio info frame and the metadata recorder. So looking at metadata, if the device just passes through the audio, then the metadata should pass through unchanged, and that's something you can check for. In terms of A to D, or analog to digital, the device should generate correct metadata that matches the audio signal. So the metadata would be, for example, a field that tells you the sample rate that's in the stream, and it should match the measured sample rate, otherwise that's an error. In terms of digital to analog, the device should read the metadata correctly so that it creates the proper analog output. Okay, we'll look at level and gain measurements. So for an A to D converter, one of the things you need to do is determine the maximum input level. And typically, you would use a sine wave at 997 hertz. The reason for the 997 is that it's not an integer divisor of the popular sample rates. And you can vary the level until the output reaches 0 dB full scale. This is the maximum input level. Some A to D converters can't reach 0 dB full scale, so you have 2 choices for defining the maximum input level. You can use the level that gives 1% THT plus N at the output using auto generator level, or you can use the level that gives 0.3 dB compression at the output using a stepped level sweep measurement. It's also possible to infer a maximum input level. So for example, you could measure the analog level corresponding to minus 20 dBFS and multiply it by 10 using auto gen level. Yeah, why don't we do a little example here. I'll set up this A to D converter and we'll do some live measurements. So we'll go back to signal path setup and set the output for digital unbalanced, the input for, sorry, the output. It's an A to D converter, so it's analog balanced out. And the input will be digital unbalanced. So we'll just see if we have a signal here. Yes, we do. So we're measuring minus 22.977 dBFS and slightly different value on the 2 channels. These have potentiometers or volume controls. Okay. So a couple of options here. We're generating 100 millivolts now. So if we crank up the signal, we'll see where we get close to 0 dBFS. Yeah, so we're into severe clipping there at 2 volts RMS. So it's just around 1.25 volts. So if we look at the references here, we could choose this control called auto gen level. And this will take whatever frequency we've selected here, and we can regulate to a measured level. So the target level would be 0 dBFS. We can choose the measured channel and then set the maximum level. Let me try something like 1.6 volts. So it's going to gradually try and find the level that gives 0 dBFS. Yeah, it looks like it's looks like it didn't go high enough. So let's, what I'll do is increase the value here to 2 volts. So it's getting pretty close there. So once it's finished, the value on channel 1 is the one that was regulated. It's at minus 0.001 dBFS. And now we could use that value. When it completes this, it sets the value of this dBRG reference, and now I can set the generator in units of dBRG, and I'll get exactly that value. And from here, I would probably go on and test at a lower level, something like a couple of dB below. Okay. Back to the presentation. So the ADD converter maximum input level versus frequency. The maximum input level can vary with frequency. So in this example, we've determined the input level for 1% THD plus N at the output. So here we're recommending that you check the entire passband. And we have a measurement called regulated frequency sweep. So at each frequency, it will generate a sine wave and vary the level until it finds the value, and it will sweep across and measure this curve. It takes a long time to measure this curve. This was done for 1% THD plus N. Let's have a look at that in APX as well. So one of the measurements we could use here is the under sweeps, stepped level sweep. And we could look at a signal from 1 volt RMS to 2 volts with a logarithmic sweep. And let's go ahead and run this measurement. So it measures the level. Here we have the gain. Next measurement is the linearity. And then the THD plus N ratio. So as you can see, we get this classic curve of THD plus N ratio versus generator level, and at some point it begins to clip and the signal rises very quickly. So we could also regulate to this point, which is 1% THD plus N ratio. Now with the measurement shown in the presentation, that would take quite a long time to do because it would be doing this at each frequency in the sweep, finding the 1% THD plus N level. Now determining the DAC output level for full-scale input. So here with the digital to analog converter, you would want to make sure the gain controls are set to the normal position. Apply a 997 Hertz 0 dBFS digital signal sine wave to the DAC and measure the RMS output level. As a check, you can apply a 997 Hertz minus 20 dBFS sine wave to the DAC, and the RMS output level should be 20 dB lower than with 0 dB. If not, something is wrong. So let's try that with this little D to A converter. So for this example, I think I'll go to bench mode. And I want to set the output to digital unbalanced, the input to analog balanced. So in this case, there are volume controls that go from minus 10 to plus 10 dB. Currently they're just set in the hard right position. I'll just leave them there for now. So we have digital unbalanced, 48K, and the input is analog balanced. And let's just turn on the generator, and we don't get a signal. So what's wrong? Are we connected? Okay, so earlier I changed the input to one channel. So we want to measure two channels. So here we're looking at the THD plus N ratio in percent. I'll switch it over to dB. And we want to set the output to 0 dBFS, or full scale. And then we have, so the level, analog level measured is 5.42 volts RMS on channel 1 and 5.1 volts on channel 2. So we could use our references here. And so let's go ahead and set dBr. We'll set dBr-A to the value on channel 1, dBr-B to the value on channel 2, and then we can add a meter here. Actually, we could change this to units of dBr-A, and then if we drop the signal by 20 dB, you can see we're measuring minus 20 on channel 1 and minus 20.5 on channel 2. So that was the little check that was recommended in the slide. So the D to A converter maximum output level versus frequency. Here you can check the maximum output level versus frequency for the flatness of the digital filter and any clipping. So you can use a 0 dBFS sine wave over the entire passband. So the graph here goes from 20 hertz to 20 kilohertz. And the scale is quite zoomed. This is it's very small, a fraction of a dB from one end to the other. So let's have a look at that quickly in the APX software. So one way to do this would be with a conventional sweep. And let's try 0 dBFS. So we have a 31-point sweep from 20 to 20K. The analyzer, by default, sweeps from high frequency to low frequency. The reason for that is the signals settle very quickly at high frequency, and it takes longer to settle at low frequency. So you can see here the RMS level. So we did a stepped sine measurement here, and for those of you that don't have APX analyzers, one of the features that's really nice in APX is the continuous sweep measurement. So here we're using a logarithmic chirp, and we're varying a sine wave very quickly. The default sweep length here is 350 milliseconds, and we can measure the frequency response very quickly. There, we just measured the chirp response, and we can it's a bit too loud. Hang on a second. Let me adjust the gain down to something more reasonable. Okay. So just to show you what that sounds like, I'll do the default sweep of 350 milliseconds. So we get the chirp occurring twice there, and what happens is the analyzer is set for auto-ranging the inputs by default. It's set to the lowest range, and when the signal exceeds that range, it'll bump up and it'll chirp a second time. So this is a very fast measurement. We get many results: the RMS level, the gain, the phase, the THD ratio. So this is total harmonic distortion, not including the noise, because it's done on a sample-by-sample basis. The THD level and the impulse response. And so as we'll note later on in the presentation, this can be used to check the polarity of a device. So for positive polarity, you can see the peak in the impulse response is positive going. If the device was inverted, we would have a larger negative going peak in the impulse response. Just turn this off. Let's go back to our presentation. And then we have digital filter response measurements. So most A to D converters have a digital anti-aliasing filter. Aliasing is caused by input tones that are higher than half of the sample rate. And they can appear in the passband, and they're not necessarily harmonic. So there are two regions of interest: the passband, where the filter will not be perfectly flat, and then the stop band, where the filter will not have infinite rejection. The stop band can be very interesting, and multi-rate filters can have bizarre responses. So for anti-aliasing filter passband response, you want to use a full-scale analog sine wave, start at a low frequency, typically of 10 hertz, and go to half the sample rate, and measure the A to D converter RMS output level. So this shows the entire passband, and there's a close-up here. Let's see. It's hard to tell the resolution on this monitor, but we can look. We can look back in the software of the measurement that we just did. So if we add a result, primary result called relative level. This shows the level relative to, it's normalized at a frequency of 1 kilohertz. And if we zoom in here a little bit, you can see the response. So you can see some ripple in the passband here that's occurring at certain frequencies. If we wanted to increase the resolution, we could use a longer sweep here. Default is 350 milliseconds. Let's try a 1-second sweep. So you can see the ripple. So for anti-aliasing stop band rejection, in this case, it would be an A to D converter RMS output. So we're sweeping here from, this is roughly about 20 kilohertz, and you can see 24K. And then this region is called the stop band. This goes, in this example, I think from 24, well, the graph here is from 20K all the way up to 192 kilohertz. So in this case, with our high-performance sine generator, we would generate a sine wave. This has to be done as a stepped frequency sweep, a step tone, and it'll start out somewhere below this, somewhere in the passband, and step the sine wave like this, and measure the RMS level all the way out to here. Now in the tech note that I talked about here for testing D to A and A to D converters, there's a step sweep that is, every step is 100 hertz. So if you go to 192K, there's roughly 1,800 steps. And it takes a very long time to do the measurement, but you do get a high resolution. If you zoom in to the transition region here, you can see greater detail in the filter response. So the analog sine generator in the APX analyzer can go up to 204 kilohertz, I believe. So an A to D converter stop band attenuation, the converter noise may make the stop band difficult to see. You can use a narrow band filter or an FFT to see the alias tones. And a tone at a multiple, at the sample rate plus or minus a fixed frequency produces a tone at F in the passband. So if we go back here, in terms of aliasing, if you had a component at some higher frequency, it would show up folded back into the spectrum because of this aliasing phenomenon. The transition region is interesting. Most converters use a half-band anti-aliasing filter with only 6B attenuation at half the sample rate. Modern converters have high internal sample rates. They have very high attenuation in the stop band, and they may not be measurable except in the transition region. For D to A converter passband and stop band, most D to A converters have a digital anti-imaging reconstruction filter. Images are copies of in-band tones above half the sample rate. And high-level images can cause problems later in the signal chain. So there are two regions of interest. In the passband, the filter will not be perfectly flat. In the stop band, the filter will not have infinite rejection. The stop band can be very interesting, and these multi-rate filters can have bizarre responses. So here for the DAC passband response, you use a -20 dB full-scale digital sine wave, start at a low frequency, typically 10 hertz, and go to half the sample rate, and measure the D to A converter RMS output level. So here we have the passband response from 20 to 24K, and then zoomed in region close-up of the passband. So you can see the ripple within the passband, which is a measurable parameter. For stop band response, you can use near full-scale signals that cover the passband and measure the DAC RMS output level above half the sample rate. The converter noise may make the stop band difficult to see. You can use a narrowband filter or FFT to see the image tones. And a tone at F in the passband produces tones at multiples of plus or minus f. Sine waves are slow, but they have high signal-to-noise ratio. And wideband signals are fast, but have a low signal-to-noise ratio. So here's a stop band response, and you can see we've generated a sine wave here at minus 20 dBFS. It's very close to the 1/2 the sample rate. And you can see the artifacts that appear at higher frequencies. And then here's a series of sine waves that are being generated. So you can see the additional components coming in as we go higher and higher. So this is a very slow process, but it gives you a lot of good information. This slide's talking about D to A converter filter overshoot and headroom. So most AES-17 tests use sine waves, but complex test signals can reveal clipping in the DAC digital filters. High-level square type waves can cause overshoot in the filters, and there may not be enough headroom. So here's a signal at minus 3 dBFS, and we have an FFT shown here from 0 to 100 kilohertz, and you can see the stop band. That's at minus 3 dBFS square wave, and if we go to 0 dBFS square wave, you get a totally different response. For measuring linearity, the step level sweep measurement can be used quite effectively. So this shows generator level on the horizontal axis and the measured level in dBFS. So voltage on this axis, dBFS on this axis, and get a straight line curve like this. And then this essentially shows the slope of this curve to determine the linearity at minus 20 dBV. This covers noise measurements. So for converter noise, all A to D converters introduce error because of the quantization. The A to D converter should be internally dithered, and the error should be noise-like. All D to A converters introduce error because of physical limitations, and the error should also be noise-like. The noise level should not vary with the signal. It shouldn't be modulated. Noise and errors are often worse at low-level signals because they're not masked by a high-level signal. And for any noise measurement, the measurement bandwidth must be well-defined because the noise will always increase with the bandwidth. So it's important when you specify a noise measurement to state the bandwidth that you're measuring over. We have a variety of noise weighting filters built into the analyzer. This shows various ones. So the solid green line, of course, is flat, no weighting filter. We have A weighting, C weighting, CCIR 1K, 2K, CCITT, and then C message, B weighting, and then some emphasis, pre-emphasis filters. So some of these weighting filters well, the weighting filters have different applications. The A weight filter, for example, is often used in acoustics because it has some relation to the perception of human hearing. And so the different filters have different applications. So AES-17 uses an RMS meter with a modified CCIR 468 or CCIR 2K weighting filter. IES 61606 uses an RMS meter with A weighting and a Q-peak meter with CCI 468 weighting. Again, when you're quantifying a noise measurement, it's important to state the weighting filter and the type of measurement, whether it's Q-peak or RMS. If you don't use a weighting filter, of course, you should specify the bandwidth of the noise measurement. So for the signal-to-noise ratio or dynamic range measurement, the converter often must be exercised when measuring the noise floor. Otherwise, the noise floor may not affect the true performance. So the AES-17 standard uses a signal at minus 60 dBFS. So it'll start by measuring a full-scale signal and then introduce a signal at minus 60 dB to keep the channel open, and then it filters out the stimulus and measures the resulting noise. So this notch filters out this low-level signal at minus 60 dBFS, and the bandwidth, it's limited to 20K. It uses the CCIR 2K weighting filter, and the RMS level is then measured in dBFS. The signal-to-noise ratio or dynamic range is the negative of this value in dB, and it's expressed as dB CCIR-RMS. In terms of noise spectra, an FFT may show unusual characteristics or problems. So here in the red we have a measured FFT with no stimulus, and you can see a very flat spectrum. And the blue curve shows a minus 60 dBV stimulus. So you see the minus 60 peak here, and then some increase in the noise at low frequencies, and quite a few of these. In the graph on the left, it's a logarithmic frequency scale, and in the graph on the right, it's a linear frequency axis. And you can see these artifacts that show up at multiples of the sample clock in the spectrum. So we have a variety of noise measurements available in APX. There's the noise RMS measurement, the noise Q-peak, which just uses a different type of detector. There's the noise recorder RMS measurement. You can record noise over a very long time. The limit on the amount of time is up to 7 days, I think. We also have the dynamic range AES-17, the signal-to-noise ratio, and of course THD plus N measurements. There are noise results available in other measurements like multitone. It has a measurement for noise density, noise level, and the total distortion plus noise ratio level and spectrum. And then of course Signal Analyzer can measure the amplitude spectral density and the power spectral density, so an FFT display of the noise.